Oh, pause and copy. I start by choosing an arbitrary element in H. Okay, so I say let P be in H. And then I'm going to apply these conditions to see what I can learn about the form of P itself. So if you're in H, that means that you are a polynomial of degree at most 3, and you pass these two tests. This test gives me this equation, and this one gives me this equation. So I got 4 variables, 2 equations. I can use a matrix to kind of reduce this as much as possible. I convert back into equations. I solve for my basic variables. And now I plug what I found here back into this P here. And the last thing I do is just collect like terms. So I collect my C terms together and my D terms together. Okay, so what have I found? I found that if you have a P and H, then necessarily it has to have this form. And what does that mean? Well, it means it's in the span of these two elements here. So if I take this whole argument all together, what does it tell me? Well, it tells me that the span of these two polynomials is all of H. So it looks like B here is going to be my basis. So all I have to do is check that it satisfies condition number 1 for a basis. So I need to check, is B independent? So let's do that now. To check something's independent, you take a linear combination and set it equal to 0. And then you try to solve for A and B. If you get just the trivial solution, then you conclude independence. Okay, so how does this work again? Let me see. I want to collect like terms on the left. So I'll put my t cubed term first, then t squared would be at squared. And then the t term would be negative a minus b. T is equal to 0. But again, this is equal to 0t cubed plus 0t squared plus 0t plus 0. So you can equate coefficients. So I can equate the coefficient here with the coefficient here, and the coefficient here with the coefficient here. And then, well, I get, B0, A0. Therefore, B is independent. Because I went looking for a solution here, and I found that the only solution is the trivial one. Okay, so we're done. Therefore, B is listed up here, is a basis. For H. Okay, another example. Find a basis for H is equal to Let's do matrices this time. A. Now, let's see. I'm going to do a similar calculation. So what I'll do is, first of all, say let x be in H, and I'll figure out what that means. Well, it means that x has to have this form. So what does that mean? Well, it means that x, if I pull it apart, I get a 1, 1, 0, 0 plus b 0, 1, 2, 2. And what does that tell me? It tells me that x is in the span of these two matrices. And if I look at this argument altogether, I can see that, oops, H is equal to the span of 1, 1, 0, 0, 0, 1, 1, blah, 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 blah. So perhaps therefore. Okay, so why does that argument do that for me? Well, what have I shown? I've shown that if I have something in H, then it's necessarily in the span. But the argument goes both ways. The arrows have two sides. So if I have something in the span, then it's necessarily in H. So what that tells me is that H is contained in the span, and also span is contained in H. So they must equal. Okay, last thing to check is that this, we'll call it B. Check that it's independent. Well, I do my usual thing. I take a linear combination. I set it equal to 0. And I see what the solution is. Well, what I get is a plus b. I get this item again. So therefore, a and b are both 0, because this has to equal this, and this has to equal this. Okay, wrapping up. What does this mean? Therefore, B is independent, and therefore B is a basis for H, because it's independent and H is equal to the span of B.